To explain the seeming contradictions between particle and wave behavior, and also the impossibility of measuring certain quantities simultaneously with perfect accuracy, and that of course was the Heisenberg uncertainty principle, Erwin Schrodinger developed the wave function, which is the Greek letter psi, in 1926. Significant work was also done by Paul Dirac, and the two gentlemen shared the Nobel Prize for Physics in 1933. In classical physics, or Newtonian physics, if all the forces on an object, that's the key, all the forces on an object are known, you can find everything else, such as position, momentum, acceleration, etc. They can all be found. They can be found using the kinematics equations, the dynamics equations. We've also assumed we can measure things to an incredible precision and then predict exactly what is going to happen, again, based on the equations that were just mentioned. Things act very differently at the very small level of atoms. We have light, which is described as a wave in a particle. We have electrons being described as a wave in a particle. And we have Heisenberg telling us there is a limit to how precisely we can measure position, momentum, energy, and time. Schrodinger conceived the idea of the wave function. This wave function is assigned to electrons and light, and they have very specific wave functions. And this performs a similar role to that of force in classical physics. If you know the forces on an object, you can tell its velocity, acceleration, other factors like that. The wave function does the same thing for these very tiny particles and light. There is a major difference, and it's underlined right over here. You can no longer exactly predict what is going to happen. You can only give the probability of something that is going to happen. The key word, probability, not exact. To emphasize again, we're not finding exactly where a particle is or what its velocity is, we're finding its probability. And to find the probability, we take this wave function psi and it is squared. This was first suggested by Max Born. And to show the beauty of this math, of the wave equation, here it is for one specific problem. This is the Schrodinger wave equation. You can see we have vector operators, an imaginary number, partial derivatives. This is very complex stuff. When you solve this equation, which should you continue on in physics, you'll be able to do when you get to college, you'll be able to understand everything you need to know there is about the particle. But again, this is college level physics, even beyond AP, but everybody should at least see this equation once when they take a physics course. The solutions to the wave equation show us how the periodic table, electron orbitals, atoms, molecules, chemical bonds, how they all work. It describes the world at the atomic level, which is so different and counterintuitive to what we see at our level. Basically, this is the fundamental drive behind chemistry. It explains everything you need to know about chemistry and how molecules are formed, how atoms combine. The uncertainty and probability concepts certainly contradict what can be seen at the macroscopic level, where we know pretty much exactly where things are and how they're moving. But that's how nature works. An example of the use of psi, the wave function, is in the double-slit experiment for electrons. Young used the double-slit experiment for monochromatic light. Again, so he had light where now we're working with the electrons. And when light was incident upon two slits, it showed a very unique interference pattern. Electrons are showing the same pattern. This leads to a key property of psi. It is used to represent all of the knowledge we have about an electron, just like in classical physics, the forces told us all we needed to know. Now, if we have a stream of electrons incident on the double slits, their wave functions, the wave functions of each and every particle, interferes with the other particle's wave functions, and also its own after it goes through the double slits. So the interference patterns are now completely explained by analyzing the various wave functions of the electrons and their interactions.